Good afternoon. This is Schweitzer. We're going to run through a major section in this particular chapter called ICE or Ice Table Calculations. Now, over the years, as we deal with some of these things, it's kind of human nature to try and memorize a whole bunch of details and of this and that. So it's important to realize to bulk information together so you're not just memorizing this type of calculation or this type of calculation or this type of calculation. That can get awfully daunting, and you really want to have confidence and start each process the same. You have a reaction x plus 2y yields z. Alright, so a couple things you might want to be aware of there, of course, is that, okay, do I have a solid? Do I have a liquid? Do I have aqueous? What things am I tracking? I'll look at my temperature, for example. The temperature is what determines K. And only way to change K is to change the temperature. So these are the things you have on your mind. Let's just say this is a solid, this is an aqueous, and this is... well, let's just go with all trackable at this point. Okay, so aqueous, everything's trackable. So we want to go through the same process every single time. You're reading over your problem. It's very common for me for a lot of years just to kind of have this ICE table. It's a holding place for information about the problem. It's really just a data table. We have initial concentrations that can be given, and we have equilibrium concentrations that can be given. Whenever you're doing these calculations, the equilibrium concentrations of x, of y, and of z can be placed directly in the equilibrium expression. And for this one, it is the concentration of z over the concentration of y squared times the concentration of x. Okay, so in this situation, you should be aware of a couple things. If they give you equilibrium conditions, then you should be aware that those are just going to go in here. Anytime you want to find a K, what do you got to do? You got to fill out the expression. Or if they give them a bunch of stuff and they want K, fill the whole table out so you can proliferate the expression so you can solve for K. Anytime you need to find K, you need to go through this process. Same thing as if we go down the line years from now, or months from now, we're doing acid base, we get a Ka, a Kb. This is for acids, this is for bases, and they say, what's the Ka of this reaction? Well, same thing. The A doesn't really matter. It's just telling me the type of a reaction that we have. But this going forward, just fill out the table of the reaction, fill up the table, and solve for K. That's the only way to do it. Again, reiterate here, temperature and this are always connected. So if I change the temperature, I change the K value. Alright. Don't memorize individual types. Be confident yourself as you go through the problem. Fill in the data table and solve for the piece you're missing. Okay, we'll walk through a couple different versions of this. A chemical process of 0.5 molar X only goes to 20% to product of X and Y. Alright, so in this situation, let's just do this. X plus Y yields Z. And I'll use that reaction. It doesn't say anything else. So initial stoic ratio. And now keep in mind, for stoic, we essentially always used moles here. And you can use moles in equilibrium, but you have to divide them all out into molarity before you use your expression. Now this one's going to be concentration of Z, concentration of X, concentration of Y. So before you can do it all in moles, before you get it into here, you have to divide everything out to get it into moles per liter. So I typically, for equilibrium, I just use molarity here. Okay. Or atmospheres if I'm doing Kp. Alright, Alright, 0.5 is the starting point. Okay, it's initial concentrations. And I got my reaction wrong, so I'm going to fix that quickly here. Alright, X goes, one more yet. Let's do this. Alright, these are my products. 0, 0. 20%, so I just go 0.5 times 0.1 is well, 20% is 0.2. Alright, and then that's what, 20% of 0.5. Pretty early in the morning, my brain's not working. And 0.1, that's... Alright, minus 0.1, plus 0.1, plus 0.1. Make sure that your stoic ratio always follows the 1, 1, 1, or whatever we have here. This is going to be 0.4, 0.1, and 0.1. Alright, now we can plug this guy in here. Typical questions might be now here it just says draw it out, but typical question might be, what are the concentrations of these guys? And what is my K value? Okay, so plug it in. 0.1. And I wrote that backwards too because I wrote the reaction wrong. So let's redo it. K equals concentration of X, concentration of Z, concentration of Y over concentration of X. Alright, so it's going to be 0.1 times 0.1 over 0.4. So you can go ahead and calculate that out. 0.1 times 0.1 is 0.01, and then divided by 0.4 is just 0.025. So K equals 0.025. Now typically, if your K is less than 1, we think of that as being reactant favored. And, you know, it is basically true, but with numbers less than 1, it is true on the larger scale. Very big numbers are product favored, very little numbers are reactant favored, but right at the cusp of 1, it can vary some. So it's close to being balanced when it's around 1. So don't take it 100% either way. So let's draw it all out. I got X here, and then it's going to be reducing down. Again, it's reducing at the same rate that I'm gaining Y and Z. Right there, Y and Z and X. Alright, next. At equilibrium, the concentration of X and Y are 0.5. Okay, so I have a new reaction here. And I'm going to just write it out, and we'll start running an ice table. Now the last one here was a pretty common example. This might be the most common example. They give you all of the reactants, and there's no products, and one product. So at that point, when you're running this thing, this thing here allows you to figure out the difference here. Sometimes when I run this thing, I could do it like this. Let's grab ourselves a new page quickly, just because I can do it this way. X plus goes to Y plus Z, initial stoic ratio end 0.500. Now, as the reaction proceeds, I will lose X of this, I will gain X of this, and I will gain X of that. And then this is given right here. This is kind of the key. Because when I know the X value, the change, then X equals 0.1. So this is 0.1, this is 0.1, and this is 0.1. And that's quite often how I would look at this problem. And it's a very common problem. At that point, I now can figure everything out, and I can solve whatever I need. This problem right here. Alright, so X plus 2Y yields Z. Now, we're giving me a K value equaling 500. So you should be aware, okay, obviously this is a K value that's product favored. Is it massively product favored? No, but still, 500 is, product favored. Start out with my ice table and see what they give me. At equilibrium, the concentration of X and Y are 0.5. So at equilibrium, this is 0.5, this is 0.5, and this is 0.1. What is the concentration of Z? Let's see here. I wrote that backwards. it says that x and y are 0.5 and 0 respectively. Okay, so this is 0.5 and this is 0.1. What is this guy? Alright, how do I figure that out? Well, let's go ahead with the K value. The K equals the concentration of Z over the concentration of Y, and that one's going to be squared, and the concentration of X. Now remember, if you get the equilibrium concentrations, they can just get plugged in here. So my K is 500 equals, and then it's going to be 0.1 squared, and then 0.5, and I'm just missing this piece. So now all I got to do is solve that piece. Multiply, square root, or I should say square, multiply over, and let's get our answer here. So 500 times 0.01 times 0.5 equals 2.5. Alright, so x equals 2.5, and this is actually unknown value x, which is really z. Z equals 2.5, and it's moles per liter. Another super common variation of how this works. Alright. What do we do if we have a really small K value? Okay. In this situation, I have 0.1, so I'll just start writing it out. 0, initial stoichiometric ratio n, we got 0.1, we got 0.1. Our place a container allowed to come to equilibrium, so there's none of this to begin with. And I'm going to lose, once again, x of this. I will lose 2x of this. Now I know this because there's no product, so I have to shift towards the product to get all items represented in the equilibrium. This is gaining x. Okay. So at the end here, what do I get? Give myself just a tad more room. Alright, so I get 0.1 minus x, 0.1 minus 2x, and then I get x. Okay, so essentially I have my K value equals the concentration of my Z, concentration of my X, concentration of of Y squared. Okay, and I want to know, okay, how, as I lose my 0.1 and I gain this guy, that's X, how much do I need to do this so that when I would match this number? 1.0 e to the negative fourth. Okay. Well, it turns out that because this is so small, that my numerator needs to be really tiny, and my denominator has to be relatively large. So how much x is going to actually change over here? Next to none. Next to none. So really, really, really tiny. So we call a shortcut rule here. Now you could algebraically solve this out, which would be in this case would be we'll try it out here. So we got x here. I'd have 0.1 minus x, and I'd have, this would be 0.1 minus 2x, and then it would be squared. So I would have a cube here, cubic. I'm not even going to be able to use a quadratic. I'd have a cubed item. So that one you could use a computer solver and your calculator to solve it out. Just plug it in and it would solve it out for you. But we do a little bit of a shortcut. And you'll find that if this number k is super small, but we say that if you are negative fourth or smaller, okay, you can use this shortcut rule. Okay? And what we're saying here is that 0.1 essentially minus this number is so small that for our intents and purposes, it's really just 0.1. And 0.1 minus 2x is really just 0.1. But all by itself, z still, we want to solve for this guy right here. Okay, it's not a subtraction or addition, it's just a lone item. So it's now present. So this is going to give us 1.0 e to the negative fourth equals x 0.1 and 0.1 squared, and x equals, and then you could solve it out algebraically this way, and you'll find that the number is just, first of all, x is really tiny. So it's a real tiny difference. So it's going to have 1.0 e to the negative fourth times 0.1 times 0.01 equals 1.0 e to the negative seventh moles per liter. So now that's my x value. So I can plug it back in, and they typically want to know the concentration of each item. So x, y, and z. I plug that value into here, so it's going to be 0.1 minus 1.0 e to the negative seventh, and we're going to say that's basically 0.1. That's how that small that value is. It'd be like 0.09000000, like 9. So we're going to say that this is basically the same thing. This also is going to be 0.1. And this guy is going to be 1.0 e to the negative seventh. Very little transferred over here. We use this idea almost exclusively in solubility for things that are, it's called KSP, for things that are really small in terms of solubility. What do we do if things are really big? Okay, and in our terms, this is really, really, really big, but for the most part, it doesn't have to be that big to be big. But I'm just going to let you know here, we got 0.1 of each. 0.1, 0.1, and 0.1 initial stoichiometric ratio end. What are, in this case, what are all the concentrations of each item? Okay. Now, in this situation, when we get really big, just that's really small. Really small, everything just basically went this way. Really big, everything basically goes this way. And we're going to treat a large K value, and it doesn't even have to be this large. You know, it could just be, you know, any really big amount is fine. But in this case, we're going to treat basically going to completion. Okay, and this just becomes a stoic question. So you go 0.1 minus 0.1 to 0 minus 0.05 to 0.05, and then plus 0.05 and this 0.05, and there we go. Okay. So all of these things are just different things you're going to see. Okay. Once you run through them once or twice, try them out, you become a pretty good expert. All right. Another example here might just find K. All right. I think I did an example like this one already. Okay, early on. Equilibrium concentrations. So give it a try. Anytime you want to find K, let's remind again. Anytime you want to find K, what do you got to do? I have to fill out the ice table, initial, stoichiometric ratio end, or I have to then proliferate the expression. Concentration of Z, concentration of X, concentration of 2Y. Alright, squared here, and this will just be that guy. Concentration of Y. Alright, and then they're just going to give it to you. Each piece just gets plugged in, and I did one like this already, so I'm not going to do another one. Okay, but they would just solve out for this guy. Another thing that is pretty common around these parts is, well, here's a practice example, I guess we're going with. Take a moment and try it out. It's very similar to the first one, but not exactly. Write the equilibrium expression, determine the Kc for the process of this thing, and draw out the representations. So pause it, try it. Okay, so we got A plus 2B yields 2C, so the Kc equals concentration of C squared, concentration of A, concentration of B, to initial stoichiometric ratio. Let's put it here, initial stoichiometric ratio end. I got so 20% again of 0.5 is 0.1. I think this is a slightly different setup here than the last one, hopefully, but 0.1. And then it says both A and B start at 0.5, okay? 0.5 and 0.5. And 20% of A goes to product, so this is 0.1. So 20% of A goes to product, which means I'm leaving behind if 20% goes to product, then I'm losing 0.1, and I'll have 0.4. I'll then lose 0.2 and gain 0.2, and now I complete the entire thing, 0.3 and 0.2. Alright, so I start out with just A and B here. A and B are both there at 0.5, let's say. And then I have over here, I like to just mark out my endings. This is your 0.5, so just guesstimate here, 0.4, 0.3, 0.2. Alright, so all I gotta do now, and of course C is down here, is just attach this part to the ending part. And I did myself proportional as best I could. So 2C just goes to 0.2, I guess like that. And then A goes to 0.4, which would be like this. Those should be relatively similar slopes, and this one should be twice that. Alright. So, just an example. And we have some examples in the workbook which you should be trying out. Alright. In a 2-liter reaction vessel, 0.5 moles of X and Y are placed at a period of time. Z measures 0.1. Okay. Go ahead and try it out. Go through all this stuff. Alright, so I got getting up over 20 minutes here, so we're going to hopefully cut this out soon, but 0.5, 0.5, nothing, initial, those are initial amounts, stoichiometric ratio end, and if Z is 0.1, so that's a pretty common method we do this, 0.1, minus X, minus 2X, plus X. Alright, X is not referred to this X, it's just general variable. So this X equals 0.1. That's what that is telling me right here. So therefore this is 0.2, this is 0.1, which is 0.4, and this is 0.3. Okay? We did this very similar setup in the last one. AC table, determine X did that, it did that. Calculate K. If you want K, you gotta fill up the expression. Alright, concentration of Z, concentration of Y squared, concentration of X, and plug your values in and solve it. I'm assuming you can do that. And finally, as we should say, we got a couple slides up, but not much. We get done here. The last main topic is to make sure that you understand how we transition from initials to equilibrium, and that's via the stoichiometric ratio. So anytime we're doing something here, sometimes they can give you a graph and say, okay, and give you several reactions. Which of these following match that? And I might stick that in here because it's a good point here. Give you one graph and say, okay, which of these matches it? So this one, for example, would look like this. If we have A and B, let's say the top, A, B, and then C, we'd note that we'd have a dropping, a double drop. That's because I got this guy here. So this is B, and then C would be picking up at about the same rate this one drops off. So they could give you this and then give you several different chemical reactions. Say, which one does this match? And we should know that this is going to match this. The slopes will match the stoichiometric ratio. And that's a little problem I've seen already. All right, and finally, okay, got one last question here. What is the following is true or false relative to these models? All right, which of the following is true? Okay, the reaction could be representing AB goes to A plus B. In this case, we're gaining two things, but I'm gaining A twice the rate at which I'm getting A. So that's not matching the stoichiometric ratio. So I'm going to say no. The reaction is at equilibrium at times both X and Y. All right, X and Y. Well, it seems like there's an issue here. I'm gonna say yes, but there's an issue here where this is a problem. Where this thing here, you can't have this guy not be at equilibrium when this one is. They both are, they both aren't. So on this line should look more like that. And I'm sure there was some done on purpose with some sort of discussion here. The reaction could be representing AB equals this, and well, the answer would be no, because it's a solid, and solids don't have a changing concentration. So 2 is the only one we're going to go with as far as, yes, they're both at equilibrium. And let's see what we put here. No, this graph is an error. Both subs hit at the same time. So yeah, so this is something that is an issue on this problem, which I've obviously stuck in on purpose, and they're all no's. But either way, it's just a matter of a thinking point. Thank you.